I'm Lorenz. So I will talk about Guppy. It's a API that we created, but first of all, I'm a Python developer. And at my company, we focus on supporting researchers from an IT point of view. And so we analyze and process a lot of data sets. And also we do some API development to create web services because all of our clients want their data on the web. And I'm the Guppy lead developer. I work at a company called Vito. Vito is a research and technology organization located in Belgium. And our goal is to come up with new ideas and solutions to help transition to a more sustainable world. We are a small part of the big company. Our team focuses on our environmental modeling. We have 6 main themes where we generate data and models for. And most of these tools are designed for the Flemish or European authorities, but we also have industry stakeholders. And so it is a little overview. We talk about why we are creating this API. We demonstrate this in 4 use cases, and we get a little feature overview, and then how you can get started yourself because it's open source. And then if we have time left, we can have some questions. So yeah, why did we develop Guppy? Because I think for having an API that just represents raster and vector data on the web, there are many of them already. But we concluded that our customers were at the beginning only just want to view the data, but more and more demand us to also do some analysis on the data in the browser itself. And then, of course, once we are going to do it ourselves, we can do more stuff with the data we already have available. And of course, the front-end developers want to have some quality of life improvements in the UI handling. So we start with the first one, and it was one of our first projects using this API. It was a European project from the DRC on fair mode, and the goal was to have a European-wide air quality map plotting all the member state maps together. So the context is, every member state has its own air quality models and they generate their own data, but we don't have one that covers all Europe in this detail. And the problem to solve there was, if we have a data viewer that stitches all these maps together, what's with the border effects between the countries? So they wanted an application to investigate these effects. So this is what it looked like, and you clearly see there's the Flemish data at the bottom part and the Netherlands at the top. And there's some kind of mistake at the border. Something's not matching up. But to see it on this picture, how much is the difference? It was hard to see. So our API just enables us, you can draw a line and you get a little graph that just samples the points on the line and the background layer to actually make this data numerical. So we can make cross-sections across the borders. There are also features that you can draw polygons to compare maps of different years. But you think, okay, this is not really that new. Why did we make it ourselves? Here's the country border effect, which is the problem in this data set. But there were little problems with these maps because, it's all of Europe. What if someone draws a line all across Europe? You can be sure that someone tries it. And then, the backend will crash probably because it goes out of memory. Or what if some country have high resolution data? We had some city level data, which was 1 meter resolution. This was like 6 years ago. 1 meter resolution was really big back then. Nowadays it's more standard. So we needed some kind of way to handle this. So there's some logic in the code that determines once you draw your outlines or your polygons or your lines, it sees how much does this line actually cover, how much pixels is this, and how much pixels do you actually need to represent your line. And then it sees, okay, GeoTIFF supports internal overviews. Which one should we select so we don't have to read in all this data and do the analysis on that? So nowadays we use a cloud optimized GeoTIFF format for that. And back then you had to just create your own overviews and make sure the dataset is tiled. And so this is how this looks inside the GeoTIFF. So it just has actually one GeoTIFF is a lot of layers on top of each other, each with a coarser resolution. And the data is then determined on which level of this resolution should we use to analyze the data. And it has a trade-off between speed and accuracy, but because we're all web-based application, we want them to be snappy because to have a nice user experience. So there was some trial and error at the beginning to see what level should we use. That the goal was to stay under half a second for every API call, whatever the user is inputting. So if you draw your rectangle or your line over all of Europe or just over your own street, it should be nearly the same time that you get the data back. Here's a little example of the consequences of this. So it's your left side. You see the 32 pixel aggregate overview. So that means every 32 by 32 pixels is averaged into 1 pixel. And then the analysis is done on it. So you see this is an air quality map of a 1 meter resolution of a city. And there's a highway surrounding a city. And there's the air quality is bad. But at the line, you don't even see that anymore because it's averaged away, the data. But if you use the 8 pixel aggregate, this peak of data is still there. And you're still processing 64 times less data than if you would use a native resolution. And if you would use a native resolution, the graph would look nearly the same because the graph isn't that high resolution on your screen anyway to show all these pixels. So it's really a simple code. It just uses the bounding box of whatever you draw and calculates with the resolution of your layer how many pixels that would be. Then we have a magic number, which is in our case 4 million. It's a bit hardware dependent. And it then determines just when the factor is your pixels divided by this magic number, and then with Raster.io you can just use this overview level, which is an integer, to give it to your open function, and you have the reduced data set. So then here we also implemented statistics for if you draw polygons, and you get these nice graphs where you can compare layers to each other. It works with a bounding box or with a polygon as a well-known text input. And it gives you a lot of statistics like minimum, maximum quantities, counts with no data, with data, and quantiles. And then we also can fetch the raw data, so the point value, which is nothing special because GeoServer can do that as well, but also line data, where you can just sample lines, sample points along a line. And this also uses these overviews to determine how many points, how long is a line, which point should I sample, and you can get these nice graphs, which also in this case compare layers with each other. But you can also get the raw data back because our API is also used internally by other APIs, not just for visualization, and sometimes they need the raw data of the GeoTIFF to calculate things that this API is doing, and also classification data. So if you have like a land use or a tree cover map, then you can see how many buildings of this type are in my polygon, what's the percentage of the coverage. So and the next part is, okay, we have all this data, we want to do more stuff with it. There's another use case. We have a 3D subsurface viewer, which our geology team, they model a subsurface in our country. And they create a lot of data which consists of 2D rasters with depth information. So every geological layer has a top and a bottom cut off in a raster layer, which represents a volume. But volume in 2D is kind of silly. So we said, okay, why don't we make 3D models from it? And you can see it actually in 3D. Okay, but they wanted to work with this data as well in a 3D model. If you want to slice it on a map, it's kind of difficult because the 3D cameras are not like a top-down view. So we implemented something to help with that, which is this is one of our 3D models. It always looks cool on a presentation. And we made a web viewer for that, where you can see this 3D model, move around in it. And they said, okay, we want to slice it in 2D as well. So what did we have to implement? You can see that these models are stacked on top of each other. So if you would look at it from the top, you probably only see the top layer and not what's beneath it. So we created an API which actually generates from the raster data the contours and then returns them as a GeoJSON back to the front end. GeoJSON is not that great of a format, so we will probably change it in the future, but back then it was the leaflet application was happy with GeoJSON. Then you get something like this, which is our viewer. You see the 3D image in a small set, and you can see this kind of makes an X-ray vision from the top to the bottom, where you can see all the different layers. And then our geologists know, okay, where exactly do I have to draw my line for the cross-section that I can see the layer that is at the bottom or somewhere in the middle. And then you can see, get a graph from the cross-section, which is just the Guppy line functionality doing its work on all these different top and bottom layers and then returning it to draw some graph for it. Another use case, which was then more advanced calculations, there was a question from a client from the government to answer a question here, where is it feasible to build underground, so with cinema complex or parking garage under the ground. And it was a lot of different input maps of which should be combined with different weights. So, but the weights were unclear. So the client didn't know how much this underground pollution has effect on this scoring, or how much do the surface is there a building already or not. So, and we thought about, okay, this is what the application looks like. You see all these options that the client can turn on, turn off, change weights, how much percent this map will contribute to the end result. So we quickly realized we can't just pre-process all of these combinations. So we should implement something that we just calculate these data on demand. So that's why our this Guppy help is we made the API that allows for mathematical operations on different layers in the backend, and then it creates a new layer to visualize in the front end. So yeah, the problem was you should add different layers, like add subsurface pollution with a different weight and some archaeology sites, and then you should subtract like sewers, heating networks, rivers. You should rescale it as quantiles or natural breaks, and then combine that rescaled result with the green protected areas that are also rescaled, and this should all be rescaled into a matrix legend. That was a requirement. And then afterwards you get something like this, depending on what the people select in the web page. The end result looks completely different, and that's what I wanted. So there's someone at his desk playing around with the weights till he's satisfied with his result, and then this gets into some political decision-making process to ensure that they can recommend, like it's for densifying cities that you can also build under the ground. So yeah. So this raster calculation API supports the combination of rasters with different algorithms like add, subtract, multiply, Boolean masks, unique products, clipping. You can also, with each step, you can apply a factor to the raster layers, and you can have some rescaling. We support now quantiles, natural breaks, equal interval, and a custom provided rescaling for this matrix legend. We had to have a custom rescale type. And the response options is, or it creates a GeoServer layer for you if you're working with a GeoServer, a GeoTIFF file directly streamed to the browser, or a Guppy layer. And then, of course, we want some quality of life improvements while we're at it. And one of the use cases was, because we are working with a lot of European projects, there is the demand for Europe has fixed color ranges for their data. So like NO2 air pollution is like from 0 to 40. But yeah, 0 to 40 is a range that works all over Europe, but it doesn't work on city level because it's much too low. And we wanted something to help with, if we change the color scale, we don't want to refetch all the data because that doesn't scale. GeoServer, which we used back then, it just has to remake all these PNG tiles with every time you change your range because the colors are different. And the cache is never hit because you are making new PNGs. It's something, it looks like this. So you have a map of a city with a NO2 deposition. From 0 to 40, you can't see anything. If you rescale it from 0 to 200, it's clear that there is some difference in the data. So it actually, the use case was we fetch a minimum maximum with the bounds of what the user is seeing, and then we apply that to the scale so we can rescale it. But in that approach, every rescale of the user triggers a refetch of the tiles, so the more people are doing that, your servers don't like it. So what we did, the problem was, so actually we wanted to serve only one tile for whatever color the user is trying to do. So we encoded the raster values directly into the PNG image. It was something like this. A float value is 32 bits, and RGBA is all the bands in the PNG, which is 4 times 8 bits. So yeah, that should fit into each other. There's one caveat that if the PNG compression notices that all your alpha is 0, you can't see anything anyway because it's all translucent. It throws away all the other information and just puts a random number that compresses good in there. So we made sure that no data is not all 0, it's all 255. So, and then the decoding of this data is handled in the browser. And then all the recoloring is done in the browser using the shader logic that's in the leaflet or in this open the MapLibre viewers, and it's really fast. You get some like funky looking images like that. That is the actual data that's in the PNG. So the downside is it's not human readable anymore, but the browser can just change the color scale to whatever you want, and there's no data refetching needed because the browser has all the raw data. So it's like you should stream the GeoTIFF itself to the browser and then it works, but now you can use the same XYZ tile servers that are everywhere and all the viewers it's all supported. And we can just use the same tile server that we are already using for other maps also for this. And then we were like, okay, we are using a lot of GeoServers. But sometimes we have projects, there's only 1 or 2 maps in them. GeoServer is a really nice application. It has a lot of features. We don't use most of them. So it hogs a lot of resources just standing there and idling. And most of the time, yeah, we had the GeoServer and the Guppy API running together. So just to serve some tiles, couldn't we just implement a simple tile server also in Guppy and said, yeah, okay, let's do it. And we wanted support to serve some basic vector and raster files as tiles, and also some basic tile caching. So yeah, what did we do? Basic functionality, it should be as fast as GeoServer at least, and it should use less resources because yeah, we are running about 100 GeoServers at our company, and they take between 1.5 to 3 gigabytes of memory, just standing there doing nothing. And the Guppy is just a simple fast API library, which runs in Python. So it takes about 200-300 megabytes of memory, and then depending on where you're caching, it will be a little bit more, but yeah, it's not in comparison to GeoServer. And also our sysad is very happy that he only has to maintain 1 service instead of 2. So yeah, we implemented it serving Mapbox vector tiles, which is actually just an SQLite file with XYZ columns and then a binary blob with the data in it. And then also we serve Raster PNG tiles, which are just, we bake the PNGs from the GeoTIFFs on the fly with a little caching mechanism that if you regress the same tile again, yeah, you just get it from the cache. And we support some basic color palettes and also this RGBA encoding on the fly. So you just request it with another SLD or a scale type, and you get these RGBA images. And while we're at it, this enables us to do some nice statistics as well. But first, it uses 3 to 5 times less memory and no separate services needed. And this is statistics that we can now generate. We just keep track of what tiles are requested. And this is an application of farmers about pesticide usage. And every farmer has to request for the government so that on which parcels he requests pesticides. And now we can see where are these farmers located that are actually using our application. And you can clearly see which are the farm areas in Belgium. These statistics can be very helpful for some projects because most of the time we have a lot of data, but we don't really know if anyone actually looks at them. We can see, okay, the cache is full, but we don't know where they are looking. So a little feature overview. So we have a basic tile server to serve vector and raster tiles and then have some statistics. Our raster statistics uses dynamic overviews to keep them fast. We can do minimum, maximum, means, quantiles, counts, and sums. For data analysis, we also use these dynamic overviews, but you can overrule it if you are really interested in the base data. You can say, okay, I always want the native resolution, but it comes with the trade-off that your calls will be slower. We can do point values, line data. For polygons, we can do raw data and classification. And then the calculations, which can be calculating the contours and then adding, subtracting, multiplying layers with each other, doing masks, clipping, and rescaling. So we decided to make it all open source. So it's on GitHub. We also made, the colleague made the Docker image too, so you can just do a Docker compose up and your server is running. We made a demo application. It's really simple JavaScript with HTML with the help of ChatGPT. The application is so just to also to show how easy it is to use, and it consists of a simple screen. You can upload your own data, and then at the back the data is transformed. So if you, for example, put a geo package in there, it generates an MB tile in the background from it. If you put a GeoTIFF in there, it makes sure that the cloud optimized format rolls out of it, and so it's ready to use. It has some little page for the metadata, so you can see what layers are in your server. You can delete them. You can add manually added data as well. So without the upload, if you say, okay, I have this file, it's already uploaded, or it's too big to process on the server itself, you can do it on your local machine and then just copy the file over and insert it in the database here. And then there's a little viewer where you can see your layers. You can draw lines, polygons, points, and also do this little calculations with adding, subtracting layers. And that's about it. Is there any questions?
Thank you, Lorenz, for this exciting talk. Do you have any questions? I guess we have plenty of time, so don't be shy.
I have a little demo of to show the speed of this RGBA encoding, which is, I can tell you whatever I want, because if you see it for yourself. This will be weird. So here you see the background layer of a nitrogen deposit. Yeah, you can't see anything because this is in Antwerp, all is red. But you have to see, here's a button. If I press it, it just takes the background, the overview. What are you seeing? Takes the minimum, maximum, or in this case the quantiles, and rescales the legend for it. If you click it, it's like floop. There, the new color. You can also type in it. You see in the background, the map is changing on the fly, because yeah, there's no refetching of data at all over the network. It's all in the browser rendering, so it's really fast. So we are really happy with this approach, and it works really good.
So I have a completely unrelated question. Why the name Guppy or Guppy? Where does it come from?
Maybe a silly question, because I was making this with a colleague, and my hobby is aquariums, and it was the only fish that the colleague knew. And there was pie in it, which was nice.
Okay, and this is backend only, so the users have to take care of the front end themselves?
Yes, but as shown, there is a little front end in the GitHub page, so which you can base yourself on. So actually, it's just the front end is just to show the map and enable the user to draw on the map. And then you just with these the things you draw, the polygon or lines, which is a well-known text, you call the API and you get answers in array data, or it's also GeoJSON or JSON format, which then can be used to draw graphs or show the data on the screen. So it's backend only, and the front end we have a separate development team for that, but it's not that hard. I made this front end and I know nothing about JavaScript, so especially with the help of the AIs nowadays, it's easy to do.
Okay. Questions? Okay, seems like we don't have any more questions. Then I would say thank you again, Lorenz, for the talk. And